Hello everybody, today I will present our paper, Fortified Multi-Party Computation, taking advantage of simple, secure hardware modules. Now, as the name already implies, this work is about secure multi-party computation, which deals with the following problem. A group of parties who do not trust each other want to evaluate some predefined function on their private inputs. For instance, these parties may want to carry out an electronic blind auction where the private inputs are the party's bids and the output is the winner and the highest bid. Another example is private set intersection, where the inputs are datasets and the output is the intersection of these datasets. Parties may also want to carry out an electronic election, where the inputs are the party's secret votes and the output is the tally. In order to solve such problems, parties need to engage in a protocol that allows them to evaluate a function on their private inputs without having to trust each other. There are also so-called general MPC protocols. These are protocols that allow securely realizing practically every purpose. In multi-party computation, one distinguishes between two corruption models. Either the set of corrupted parties is fixed prior to the start of the protocol execution. This models protocol parties conspiring before the protocol has started, or parties may become corrupted at any point during the protocol execution. This intuitively models remote attacks, where adversaries or hackers break into computers during the protocol execution by, for instance, sending computer viruses. Up to now, all MPC protocols leak the private inputs of the parties corrupted during the protocol execution. This also holds true for protocols that allow the parties to erase their local data. In this case, the adversary has to corrupt such parties before they have erased their secret local data. As a consequence, all previous MPC protocols are susceptible to remote attacks. That is, an adversary may learn the party's private inputs and therefore sensitive information by sending remote attacks. In this work, we present general MPC protocols with very strong security guarantees against remote attacks. The parties in our protocols do not necessarily leak their private inputs if they are corrupted during the protocol execution via remote attacks. In more detail, if a protocol party in our constructions has already received input and is corrupted during the protocol execution by a remote attack, then this allows the adversary to gain full control over this party, but not the ability to learn the party's private input, nor its private output, nor to modify its input or output unless all parties are corrupted. These strong security guarantees against remote attacks hold even in the concurrent setting, where our protocols may be executed concurrently with arbitrary other protocols. Now, our constructions are based on the following observation. In practice, parties may be temporarily isolated and therefore not remotely hackable, at least not at any point during the protocol execution. For instance, parties may utilize air-gap switches, which act as drawbridges, isolating parties from the network. Or parties may implement unidirectional channels with so-called data diodes. In addition, parties may also utilize other simple remotely unhackable hardware modules, such as a encryption module that simply implements a specific public key encryption scheme. Such modules can be implemented as fixed function circuits and verified for correctness. It may therefore be assumed to be remotely unhackable. In our work, we therefore propose a new security framework called UC, or Universal Composability, with fortified security. Our new framework comes with a new corruption model where one distinguishes between physical attacks and online attacks. Physical attacks model adversaries tampering with hardware. Online attacks model remote attacks. Online attacks are only effective if the targeted party is what we call online, that is, able to receive messages and remotely hackable. In the following, I will present a simplified version of our constructions. But before giving the protocol description, recall our security goal: an adversary mounting online attacks against a party who has already received input may not learn that party's input or output, nor may he be able to modify that party's input or output unless all parties are corrupted. So in our protocol, each party utilizes three hardware modules: a buffer, a so-called encryption module, and a so-called output interface module. The encryption module and the output interface module are assumed to be remotely unhackable. The buffer and the party itself, being for instance a personal computer, may be remotely hackable. Our protocol proceeds in several phases. In the first phase, parties are offline and only communicate through their encryption module. In this phase, each party computes shares of its input, and as will be explained later, also of other things. These shares are then encrypted using their respective encryption module, together with signatures of these shares and the intended receiver's identity. This ensures message authentication. These ciphertexts are then sent to the other party's buffers. Note that since each party is offline in this phase, it may not receive messages itself. Now, once this phase has been completed, each party erases everything except for its own share, its encryption key, and the public keys. Note that since the parties have shared their inputs among each other in this phase, the adversary has to corrupt all parties in order to reconstruct the party's inputs. Therefore, an adversary who mounts online attacks against a party who has already received input is not able to learn that party's input unless all parties are corrupted. In the next phase, called compute phase, parties engage in a multi-party computation. The input of this multi-party computation are the shares and signatures the parties received in their buffer and the signature verification keys of each party. The result of this multi-party computation is the following. If all signatures are valid, the desired function value is the result of this protocol execution. Actually, it's a bit more complicated, as I will explain later. Otherwise, if any signature is invalid, the output of the protocol is error. If the adversary corrupts a party during the protocol execution by mounting an online attack and instructs that party to modify some of its shares, then this would, of course, modify the inputs, the input of some party or several parties. But since the signatures are invalid if the adversary modifies any share, the result in this case is error. This also holds true, of course, if the adversary instructs a party to modify the share of its own input. Note that since the signing key has been erased, the adversary is not able to create signatures of shares he created himself. Therefore, if the adversary corrupts a party who has already received input through an online attack, he's unable to modify that party's input unless all parties are corrupted. In the final phase of the protocol, the so-called output phase, the output of a party is handled not by the party itself, but by its so-called output interface module. This is motivated by the following. A party could have been corrupted via an online attack during the protocol execution. Therefore, its output is not trustworthy, since it may have been manipulated by the adversary. However, the output of the output interface module is trustworthy, since this module is remotely unhackable. To see how this output interface module works, we need to go back to the sharing phase. In the sharing phase, each party sends a symmetric encryption key together with a key for a MAC, message authentication code, to the output interface module, and this distributes shares not only of its input, but also of this symmetric encryption key and also of this MAC key, along with a signature on these shares. In the compute phase, the parties, as mentioned before, engage in a multi-party computation using as inputs the received shares and signatures and the verification keys. Now, the result of this multi-party computation is the following. If all signatures are valid, the result is the desired function value encrypted with the respective symmetric encryption key, together with a MAC tag of this encrypted function value. Now, if an adversary corrupts a party during the protocol execution through an online attack, then he only learns the encrypted function value. And since the symmetric encryption keys have been shared among the parties, he would have to corrupt each party in order to learn the function value in the clear. Therefore, if the adversary mounts an online attack against a party who has already received an input, he is unable to learn the party's output unless all parties are corrupted. Finally, in the output phase, each party sends the encrypted function value and MAC tag it has received in the compute phase to its respective output interface module, who will then verify the MAC tag, and if the MAC tag is valid, will decrypt the function value and output the result. Otherwise, if the MAC tag is invalid, the output interface module will output error. Note that since the MAC keys are shared among the parties, the adversary again has to corrupt all parties in order to learn the MAC keys. Therefore, if the adversary mounts an online attack against a party who has already received input, he is unable to modify that party's output unless he corrupts every party. In the final section of this talk, possible implementations of the remotely unhackable hardware modules used in our protocol are presented. First, 3 important remarks. The remotely unhackable hardware modules used in our protocol only have to be trusted by their owner, do not have to be sent to other parties, and only have to be secure against remote attacks. Therefore, they do not have to be tamper-proof. Now, an air-gap switch can be implemented using any managed Ethernet switch, or alternatively, a non-managed Ethernet switch together with a remotely controllable power strip. There also exist various open source DIY implementations for data diodes, for instance, the so-called tinfoil chat. These implementations exploit physical principles and therefore require very little trust. Concerning the implementation of the encryption module does not have to handle secret keys, since it only uses public keys, which are retrieved from the public infrastructure. The public keys retrieved from the public infrastructure, of course, have to be verified. That is, their integrity has to be verified. This can be done by using, for instance, certificates. The encryption module can be implemented using an hardware security module together with a simple network interface. Finally, concerning the implementation of the output interface module, the output interface module only provides an interface for outputs. Therefore, no network capability is required, unlike in the case of the encryption module. Therefore, the output interface module can be implemented as follows. One can extend an HSM or an FPGA with the required functionality and connect it via some interface providing a secure output. For instance, one could use a simple dot matrix display. Okay, let me summarize. In our paper, we constructed general MPC protocols providing very strong security guarantees against remote attacks. These protocols are proven secure in a new security framework, which we call UC, or Universal Composability, with Fortified Security, which comes with a new corruption model that distinguishes between physical attacks and online attacks, the latter modeling remote attacks. Okay, so thank you for your attention.